Hello again, wonderful physics students. All right, we're going to continue our discussion on momentum with some big ideas on momentum. These are three ideas. Elastic collisions. Now, elastic collisions are like pool balls. If two pool balls hit each other, they bounce off each other. Neither ball is damaged. So whatever momentum this ball has coming in this way is transferred to the other ball. Whatever momentum this ball has coming in this way is transferred to the other ball. So the momentum is just swapped between the balls when pool balls collide. That's an elastic collision. Now you can tell it's elastic because neither object is damaged. They generally bounce off each other. That would be an elastic collision. The other kind is an inelastic collision, and that's where, say, a bullet hits a lump of clay and they stick together, right? So an inelastic collision, both objects stay stuck together. A lot of energy is used in sticking them together, and because momentum is a vector quantity, you just add the two momenta together, considering positive and negative signs. Whatever is the leftover momentum, positive or negative, tells you which way the object is moving, carrying that momentum with the new incorporated masses of both of them. That's an inelastic collision. I'll show you how to do both of these. The other one is a universal equation, and it's awesome. I term it as pin equals pout, because you'll remember it. If I take a pin and poke you, I bet you'll pout. Pin equals pout. And what that really means is P in equals P out. Now that's not disgusting. P stands for momentum. This is not biology. P in, that means the momentum in is going to be the momentum out. So all you have to do is collect all the momentum you can find out about coming in. That must equal all the momentum you can find out about plus the unknown going out. So pin equals pout. And that's a very powerful one. And if you look at equations and stuff, it'll make you crazy because it looks very complicated. It's really not. Momentum in is momentum out. That's it. So we're going to use that. Let's start off with an elastic collision. These are kind of sweet. Check these out. So let's have a 4-kilogram object. Now, pay attention to where I write the notations. It'll help you a lot, make this stuff easier. I have a 4-kilogram object moving at 3 meters per second to the right. Okay, what's the momentum of that? Well, momentum, P equals mv. So what's the momentum of that? Good. Write it right on top. 12 kilogram meters per second. All right. That's going to collide with a 9-kilogram object moving at 2 meters per second. And this collision is going to be elastic. All right? It's going to be perfectly elastic. Now, perfectly elastic collisions don't really exist, but they get so close that within significant figures it's fine. But if you hear the balls tap against each other, does that mean some energy was subtracted? Yeah. Do the balls heat up where they tap against each other? Yeah. So energy is subtracted that way. But we could think of it as elastic, like elastic for the most part. So what's the momentum of this going to be? Well, mass times velocity, it's going to be 18 kilogram meters per second. And you notice I put these numbers on top of vectors. These are vector quantities. That's pretty important. Now, I'm just indicating right and left, so I don't need to use negatives. But which one of these would be negative if I need to use it? Well, the one going to the left, right? Remember, there's something wrong with left-handed people. That's the way they used to think. We need physics, all right? So this would be negative, but I'm not going to put negative on it when I'm already showing it, because otherwise it might be confusing. It might act like a double negative, and you might think it's going the other way. So we're just putting it like this. Now, the question is, what is going to be the status after the collision? What's the status of this 4-kilogram object? Okay, what's the status of the 4-kilogram object? What's the status of the 9-kilogram object? Well, this is easy. The momentum transfers. So this momentum from the 4-kilogram object, this momentum was going to the right. It stays going to the right, but now it's going to be carried by the 9-kilogram object. So that 9-kilogram object is going to be carrying a momentum of 12 kilogram meters per second. Well, 12 kilogram meters per second. How does a 9 kilogram object carry a momentum of 12 kilogram meters per second? Do you see how the units work out? If I just divide kilogram out here, I'm left with meters per second. This diagram really makes it easy. So if I take 12 divided by, if I clear it, 12 divided by 9, there you go. This must have a velocity to the right of 1.3 meters per second. In order to carry that 12 kilogram meters per second of momentum that was being carried by this, now by a 9 kilogram object, that simply has to move at 1.3 meters per second. Similarly, this 18 kilogram meters per second is all going to be transferred to the 4 kilogram ball. So, 18 kilogram meters per second continues to move to the left. Now it's carried by a 4 kilogram object. So we take 18 kilogram meters per second divided by 4 kilograms. The kilograms cancel out, and I see a velocity of 4.5 meters per second. That's it. Elastic collisions. They're kind of fun. The momentum transfers from one object to another. So the two objects bounce, and they both go off carrying each other's momentum at whatever velocity they need to do to carry that momentum. So that's elastic collisions. All right? I'm going to make another video on inelastic collisions, just so you don't have to watch the whole thing right here. All right? Hey, thanks for watching.